Stop worrying about homework and start learning with confidence. This is Ask Learn. Complete help for every subject. Like, share, subscribe for daily learning videos.
Okay, so for this problem, let's try to get an understanding of what's going on here. So, we're told that we have two coils in a magnetic field that are rotating in this magnetic field. So, it's a good idea that we're probably going to have to use our equation for torque, which is tau is equal to N is the number of coils times the current in those coils times the area times the magnetic field sine of theta. So now what exactly do we have going on in our situation? So we have two coils. They are separated in the middle. So we've got one coil here, one coil here, and these are in a magnetic field that is present throughout. So what this area here means is, so imagine these coils, or these wires here have wrapped wires around them that just twist all the way around. So there's wire wrapped all the way around these long wires. And the number N here is the number of loops of wire. So the reason we have this N with this A is that what this area is imagine, so this is a real thin coil. If we blow this up, the front end of it looks like a circle. Now imagine, so this is the wire. This is just a blown up version of the tip here. So now this has a radius, and that's what we mean by area, is the area of this circle times the number of loops, which is this N. So that's how many loops this has going around. So the more tightly packed these loops are, the bigger our torque is going to be, the more force there's going to be in this whole system. So that's why we have an area here. Now the area of this circle, the area of a circle, if you recall, is equal to pi times the radius squared. That's the area of a circle. So if we take the area of one circle and multiply it by the number of loops, how many times this wire bends around, we get the total force that will involve this current. Now another point of note here is we're told that they have, each of these wires has the same maximum torque. And what that means is that when this torque hits this magnetic field, so these will be spinning around, say, this way. This will be maximum when it is at a point where the magnetic field, the force from the magnetic field, is completely perpendicular to the point of contact here, or to the wire. So at this point here, it'll be completely perpendicular to this magnetic field when it is straight down. And in this case, it'd be the opposite, straight up. So that means that our angle at the highest possible magnitude is when this theta here is equal to 90 degrees, when they are perpendicular. Which means that the sine of theta will be 1, so we won't really have to worry about that in this equation. Okay, so we are told that they both have the same number of coils, they both have the same current, and they're both in the same magnetic field. And they have the same maximum torque, which is where we get this 90 degrees from. So we can write two equations that involve all these factors. We can write one for the first wire and one for the second wire. But everything is going to cancel out. And this A here is this. This is what's equal to A, this pi r squared. So if we have all the same things on each side, the number of coils are the same, those will cancel. The currents are the same, those will cancel. B's are the same, and those will cancel. So all we're left with is... No, the B's are not the same, sorry. We have different B's, different magnetic fields on each side. So, actually, there is a cutoff here with different magnetic fields on each side. So that's something we'll have to keep in this equation. So we've got different magnetic fields and different radii, and this pi will cancel out. So this is the equation that we'll end up having. So we don't need tau because we're told that they have the same torque, the same maximum torque. So we can set this equation for the first one equal to the equation for the second one, like so. So we have n's the same. I'm not going to subscript those. I's the same situation. We have the area, which is pi r squared, but we have different radius. So I'm going to call this one radius 1. That's A. We have a different magnetic field, so this will be B1 to correspond with R1. This is equal to the same equation for the other wire. We have N, I, pi r squared, but this time we'll have a R2. R sub 2 squared, which is the area for the second wire, times the second magnetic field. So now we can cancel all this stuff out. That's the same on both sides. Number of coils and the current is the same. We each have a pi. Each side has a pi. So what we're left with now is R1 squared times B1 is equal to R2 squared times B2. Okay, so we are given both of the magnetic fields. We know what they're equal to on each side. We are also given what the radius of the first coil is. So we have an equation here with one unknown, in which case we can solve for it. R2 is equal to the square root, because we had r squared. I'm just going to skip ahead here and take the square root of the whole thing, is equal to divide B2 by both sides, so we get R2 on its own. We'll get the other side, R1 squared, times B1. The magnetic field the first wire is in, B1, divided by the magnetic field for the second wire, B2. And this is all under the square root. And this will give you your radius for your second wire. And another point to note, the first radius is given in centimeters, but the required answer that they want is also in centimeters, so you don't have to worry about doing any conversions. You can just plug in your R1 in centimeters. You don't have to convert that. And that'll give you your answer.